Okay, integral applications. There's three big fields for applications of integrals. One of them is finding average values. One's finding area, which we've seen a little bit of. And the third is finding volumes of complicated shapes. So we're going to start with average value. We're going to start off pretty simple with it. You remember that when we found an average of discrete values, you just add them up and divide by the number of values. For example, if you had 1, 5, 6, you'd add them up and divide by the number of values, which was 3. That finds the average value. So we need to figure out a way to do this with functions, a continuous set of values. So we need to find the total sum of all the values and divide by the number of values. So use this to find the average value that a velocity travels for a trip from 1 to 3 hours in the following scenarios. First of all, note what the following would represent in terms of the problem if we're averaging velocities. So the total of all the values would be that'd be the total distance traveled. Total distance traveled. Number of values for finding the average velocity would be the total time. So, first scenario. Car is set on cruise control at different speeds each hour. So the total sum of all the values. Okay, so here, 5 miles per hour for an hour would be 5 miles, plus 15 miles per hour for an hour would be 15 miles. So the total would be 20 miles. And the number of values, that was over 2 hours. So that's 20 miles in 2 hours, which is an average velocity of 10 miles per hour. Now, does that make sense in this situation? You went 5 miles an hour for an hour, 15 miles an hour for an hour, average is 10 miles per hour. Makes sense. Now let's set cruise control differently each half hour. So these are half hours. So we went 5 miles an hour for half an hour, 2.5 miles. And then 10 miles an hour for half an hour. And then 15 miles an hour for half an hour. And then 10 miles an hour for half an hour again. So our total sum of the values would be, let's see, 10 and 10, 20 miles. And a half hour, half hour, half hour, and a half hour, 4 times a half hour gives me 2 hours. So we went 20 miles in 2 hours. So we're averaging 10 miles per hour again. Makes sense again? Let's go every quarter hour. I may have to show a little bit more work on this one. Quarter hours. Woo. Changing speeds a lot. Oh, these are not great rectangles. No judgment. No judgment. Okay, so for the first quarter hour at 5 plus quarter times 10 plus a quarter times 15 plus quarter times 10 plus a quarter hour for 5 hours plus quarter hour for 10 plus quarter hour for 15 plus a quarter hour for 10. Could I add up all the values and then divide by 4 here? I think I can. 5, that's 15, 30, 40, 45, 55, 70, 80. Divided by 4 is 20. 20 miles again? Number of values. We had a quarter hour, and we have 1, 2, 3, 4, 5, 6, 7, 8 divisions of those, so that's 2 hours. So again, 20 miles in 2 hours. That's average of 10 miles per hour. Now, each scenario above, the number of values is the same, right? Could we have done that a little differently? Well, it was 3 minus 1, huh? So let's think. Yeah, we could have just taken the 3 minus 1 and gotten the 2 hours that way. So integrals are finding the infinite sum of values. So we can use the integral to find the total sum of all the values. So the average value of a function would be the total sum of values from A to B of f of x dx divided by b minus a. Like here, we're dividing by the change in time. Let's see some examples. Find the average value of f of x equals x squared minus 2x on 1 to 4. It's the integral from 1 to 4 of x squared minus 2x dx divided by 4 minus 1. Finding the average. Well, I know I need to take the antiderivative. So the antiderivative of x squared is going to be x cubed divided by 3 minus 2, that's going to be x squared divided by 2, that's just going to be x squared, evaluated from 4 to 1, divided by 4 minus 1, which is 3. So we need to plug in 4 minus the integral evaluated at 1. And then divide by 3. So let's see, 4 cubed is 64, so that's 64 thirds minus 16. That's going to be minus 1 third minus a negative 1, which is going to be plus 1. Let's see if I can clean that up any. Let's see. 60, ooh, I can't count. 63 thirds minus 15 divided by 3. Oh, 63 divided by 3 is 21. So 21 minus 15, I'll write it over here. 21 minus 15 divided by 3, that's going to be 6 divided by 3 is going to be 2. Average value of cosine from pi to 2 pi. Average value means we need to divide by that change in x's. So, integral of cosine is sine. We're going to evaluate it from pi to 2 pi. And then divide by the change in x's, which is just pi. Well, this one's interesting. The sine of 2 pi is the same as the sine of 0. That's 0 minus the sine of pi, which is 0 divided by pi. Average value is 0. And why does that make sense? Because we had areas above the curve and below the curve. Bill can paint walls at a rate modeled by V of t equals 200 minus 4t, square feet per hour. T is the number of hours since he started painting. What is the average rate at which he can paint the walls in the first 10 hours of the job? Integral from 0 to 10, first 10 hours, of 200 minus 4t divided by the change in time. So, oops, I forgot dt. So the antiderivative there would be 200t minus 2t squared, evaluated from 10 to 0, divided by 10. What's going to happen when I plug in 0? Nothing. So, 200 times 10 minus 2 times 10 squared. 10 squared is 100. 2,000 minus 200 is going to be 1,800 divided by 10. It's going to be 180 square feet per hour, because we're dividing by the hours. Next, following table gives the average monthly temperatures for Hot Springs, Arkansas. So we're asked to find the average of the monthly temperatures, which is fairly easy. We're going to find the sum of the temperatures divided by 12. So to kind of speed things up, I've already typed in all those temperatures into my calculator. 885 divided by 12, and I get 73.75. Approximately 74. Now, if we're going to model with a trig function, let's remind ourselves some things. Okay, so we've got temperatures starting out like at 51, and they're going up. They're at 74, which is about the average in April. So here is in January. And then it gets up to its peak in July. And then by about, let's see, around October it was at 76 again. And then it starts to head toward the bottom. So could that be done with a trig function? Why, sure. I just need to figure out how to write it. So gosh, I got to remember some trig stuff. I got to think about amplitude and think about that, how it's been shifted to be able to write that. So let's see. This is about 73.75. Is that going to be a good average? Well, let's see. If I go from around 74 to 95, that's 21. If I go the opposite direction, it's about 21. So I'm going to say my amplitude is approximately 21. Period. Well, period here is going to be 12 months. Normally it's 2 pi. So 12 divided by 2 pi. You know what? I'm second guessing myself. So if you ever forget, okay, so 2 pi over b equals 12. So b, I had it backwards, is 2 pi divided by 12. See, I knew I had it backwards. Okay, normally cosine starts at the top. So my shift over is around 7. So c is 7. That'd be pi over 6, x minus 7. And the shift up is the shift of this horizontal line, which would, I'm going to put in at about 74. So for this one, let's actually use our calculators to evaluate. We're going from 0 to 12 of this function, which I hope I typed in well. Dx. And then we're going to divide that by 12. So to do it in your calculator, we're going to do alpha f2, the integral from 0 to 12. And then I type in my function. Oh, I better make sure I'm in radians. I am. So 21 cosine of pi over 6 times x minus 7 I need to close parentheses again, plus 74 dx. 888 divided by 12 gives me 74. So they're about the same? Which one do you think is actually the better true average monthly high? And this one's an interesting one. Suppose the average value of the function f of x on 1 to 5 is 10. Let g prime equal f of x and g of 1 equals 7. Then find g of 5. Crazy sounding, right? Okay, so let's start at the beginning. Average value, so from 1 to 5 of f of x dx divided by 5 minus 1 equals 10. Well, let's see, that's 4. So the integral from 1 to 5 of f of x dx equals 40. All right. Well, now it tells me g prime is f of x. Well, the antiderivative of a derivative is the original. So I'm going to be evaluating from 1 to 5. So this is going to be g of 5 minus g of 1 equals 40. Aha! They give us g of 1. So, g of 5 equals 47. Nifty.